Hello. In this video we will discuss Newton's third law of motion, and we will solve a cool physics problem that makes use of all three laws. Newton's third law states the following. Whenever object A exerts a force on object B will exert a force of equal magnitude on object A, but in the opposite direction. So if A pushes B, B will push back just as hard. This is always true and is automatic. Think about a simple example. When you try to push something heavy, you are exerting a force on it, but you also feel it resist your attempt to move it. The resistance is the force that it is exerting back on you. Go ahead, try to push something right now. The way that this law is often stated is as follows. For every action, there is an equal and opposite reaction. Equal because it's equal in magnitude, and opposite because it is opposite in direction. To understand the consequences of this law, let's think carefully about the following scenario. Imagine I am trying to push a car. Because a car is so massive, I will have to push very hard on the car to get it to move. But that means the car will be pushing hard on me, enough to make me accelerate backward. To prevent that, I will dig into the ground as much as possible. This works because I will be exerting a force against the ground in this direction, so the ground will exert a force on me in the other direction. Now, the ground is exerting a force on me, and the car is exerting a force on me. And if I push against the ground hard enough, those forces will cancel out. In that case, I will not move, and hopefully the car will, since it does not feel another force to cancel out my push. I realize this is confusing, and you probably haven't thought about things this way before, so I suggest you go back over this example again. This is a really important concept to understand, and will help you make sense of a lot of real-world situations. So let's now look at an example that will require all of Newton's laws to solve. Imagine you are an astronaut floating in space. You want to get back to your spaceship, which is to your left. Floating next to you on your right is a crate. How do you get back to your spaceship? Well, because of Newton's third law, you know that if you push the crate to the right, the crate will push you to your left. That's perfect, because that is the direction of your spaceship. So to accelerate towards your spaceship, you need to push the crate to the right. Once you stop pushing, you will stop accelerating, and you will maintain a constant velocity, drifting in space. So let's actually calculate how much you will accelerate towards your ship given a certain amount of pushing force. To solve this problem, we will not use numbers. Rather, we will just use symbols to represent all the factors that are involved, and we will get an equation of your acceleration in terms of all the other factors, including the pushing force. So to begin, we will redraw the situation to make things a bit simpler. You are now a boring square, as is the crate. We will give you each a letter. U can be Y, and the crate can be C. We now mark that you have a mass of m sub y, and the crate has a mass of m sub c. You can read this as the mass of y and the mass of c. Now we want to solve for your acceleration, which we will label as a sub y. Finally, we should choose a sign convention, which means that we will treat the rightward direction as positive and the leftward direction as negative. What we have here is often called a free body diagram, and the idea is to take some complex, real-life situation and simplify it into boxes and letters that we can easily work with. So if you push on the crate, then you exert a force on the crate away from you, which is towards the right. We write that like this, an arrow representing the force vector, and we have to label it somehow. I will label it like this, F with a subscript of Cy, which I read as the force on C from Y. So now our diagram includes my push. Since we are in space, no other forces are acting on the crate, so let's move on and draw the forces acting on you. Since you are pushing the crate, it is pushing you, so we draw this force vector in the opposite direction, with the same magnitude, which I will label F sub yc, which we read as the force acting on you from the crate. Wonderful. We now have our diagram. Next, it's time to write out some equations. First, the two forces are equal and opposite, so we can write that like this. F sub yc equals negative F sub cy. Second, we want your acceleration, so we will use Newton's second law to write that your acceleration equals the force acting on you, which is F sub yc divided by your mass. Great. Now we said that we wanted to know your acceleration in terms of the push you gave the crate, which is F sub cy. So using this formula, we can substitute F sub yc for negative F sub cy. This means we end up with this formula here, which in normal English says that your acceleration will be the force you push with divided by your mass. The negative sign means you will accelerate leftward. Great. That is everything we wanted to know. We applied the action-reaction law, and we applied force equals mass times acceleration to get a real useful physical result. And that's it for this video. Thanks for watching.